In a four-wire system, the primary overcurrent protection may not provide secondary conductor protection due to the neutral current path. In a three-phase system, a neutral current is the vector sum of the three-phase currents. If the secondary load is unbalanced, the neutral current can be greater than any of the phase currents. The primary overcurrent protection is only designed to protect the primary conductors, not the secondary conductors. Therefore, it is recommended to provide separate secondary overcurrent protection, even when the primary has 125% protection. This is a common requirement found in local electrical codes and industry standards, such as the National Electrical Installation Standards. A maximum secondary conductor length can be determined using the following formula: L equals Z times I divided by V times PF, where L is the maximum conductor length in feet. C is the impedance of the conductor in ohms per 1000 feet. I is the maximum load current in amps. V is the voltage of the secondary system in volts. And PF is the power factor of the load. To further elaborate on the concept of transformer secondary conductor protection, especially in four-wire systems, let's delve deeper into the nuances and considerations involved. We'll explore the reasons why relying solely on primary overcurrent protection for secondary conductors can be problematic, the implications of neutral current, and practical steps for ensuring adequate protection. We will also cover the calculation of maximum secondary conductor length. Firstly, consider the fundamental purpose of overcurrent protection. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical conductors from damage caused by excessive current flow. This excessive current can result from various factors, including short circuits, ground faults, and overloads. The primary function of these devices is to interrupt the circuit when the current exceeds a predetermined threshold, thereby preventing overheating, insulation breakdown, and potential fire hazards. Now let's examine why the primary overcurrent protection may not adequately protect secondary conductors in a four-wire system. The key lies in the behavior of neutral current in such systems. In a balanced three-phase system, the neutral current is ideally zero. However, in real-world scenarios, loads are rarely perfectly balanced. This imbalance leads to a non-zero neutral current, which can circulate through the neutral conductor. The magnitude of the neutral current depends on the degree of imbalance among the phase currents. Under certain conditions, the neutral current can exceed the current in any of the individual phase conductors. This is particularly true when dealing with nonlinear loads such as electronic devices and fluorescent lighting, which generate harmonic currents that can significantly contribute to neutral current. The primary overcurrent protection is typically sized based on the transformer's primary current rating and the allowable overload specified in the relevant electrical codes. This protection is designed to protect the transformer itself and the primary conductors feeding it. However, it may not be sensitive enough to detect overcurrent conditions in the secondary conductors caused by excessive neutral current. Because the primary overcurrent device sees a transformed value of the secondary current, it is possible for a large neutral current to exist on the secondary without tripping the primary protection. This scenario can arise when the secondary load is significantly imbalanced, resulting in a high neutral current that is not reflected proportionally on the primary side. Furthermore, the impedance of the transformer windings can affect the coordination between the primary and secondary overcurrent protection. The transformer's impedance limits the fault current that can flow during a short circuit or ground fault on the secondary side. This impedance can reduce the magnitude of the fault current seen by the primary overcurrent device, making it less likely to trip and clear the fault quickly. To address these challenges, it is crucial to provide separate secondary overcurrent protection for the secondary conductors. This protection should be sized and coordinated to protect the secondary conductors from overcurrent conditions, including those caused by excessive neutral current. The secondary overcurrent protection can be implemented using various devices, such as circuit breakers, fuses, or molded case switches with fuses. The selection of the appropriate device depends on factors such as the secondary voltage, current rating, interrupting rating, and coordination requirements. In addition to providing overcurrent protection, It is also essential to consider ground fault protection for the secondary system. Ground faults can occur where a phase conductor comes into contact with a grounded surface, such as a metal enclosure or conduit. Ground fault protection devices, such as ground fault circuit interrupters or ground fault relays, are designed to detect and interrupt ground fault currents, thereby preventing electrical shock hazards and equipment damage. Now let's discuss the calculation of maximum secondary conductor length. As mentioned earlier, the maximum conductor length can be determined using the formula L equals Z times I divided by V times PF. This formula takes into account several factors that influence the voltage drop and current carrying capacity of the conductor. L represents the maximum conductor length in feet. This is the maximum distance a conductor can run before the voltage drop exceeds an acceptable level. The acceptable voltage drop is typically specified in electrical codes and standards such as the National Electrical Code. C represents the impedance of the conductor in ohms per 1000 feet. The impedance of a conductor is a measure of its opposition to the flow of alternating current. It consists of two components, resistance and reactance. Resistance is the opposition to current flow due to the conductor's material and dimensions. Reactance is the opposition to current flow due to the conductor's inductance and capacitance. The impedance of a conductor depends on its material, size, and temperature. It can be obtained from conductor tables or calculated using the appropriate formulas. I represents the maximum load current in amps. This is the maximum amount of current that the conductor is expected to carry under normal operating conditions. The maximum load current should be determined based on the connected load and any applicable directing factors. V represents the voltage of the secondary system in volts. This is the nominal voltage of the secondary system, such as 120/208 volts or 277/480 volts. PF represents the power factor of the load. The power factor is a measure of how effectively the electrical power is being used. It is the ratio of real power to apparent power. A power factor of 1 indicates that all of the electrical power is being used effectively, while a power factor of less than 1 indicates that some of the power is being wasted. The power factor of a load depends on the type of load. Resistive loads, such as heaters and incandescent lamps, have a power factor of 1. Inductive loads, such as motors and transformers, have a power factor of less than 1. Capacitive loads, such as capacitors, have a power factor of less than 1. To calculate the maximum secondary conductor length, you need to determine the values of Z, I, V, and PF for your specific application. You can then plug these values into the formula and solve for L. For example, let's say you have a 120/208 volt, 3-phase transformer with a secondary load of 100 amps and a power factor of 0.8. You are using copper conductors with an impedance of 0.5 ohms per 1000 feet. The maximum conductor length can be calculated as follows: L equals 0.5 times 100 divided by 208 times 0.8 equals 0.3 feet. Therefore, the maximum secondary conductor length in this example is 0.3 feet. It is important to note that this formula provides an estimate of the maximum conductor length. In practice, you may need to reduce the conductor length to account for factors such as ambient temperature, conductor bundling, and conduit fill. You should also consult the relevant electrical codes and standards to ensure that your conductor installation complies with all applicable requirements. In addition to the formula above, there are other methods for determining the maximum secondary conductor length. One common method is to use voltage drop tables, which provide the voltage drop per unit length for various conductor sizes and current levels. These tables can be used to determine the maximum conductor length that will result in an acceptable voltage drop. Another method is to use voltage drop calculators, which are available online or as software applications. These calculators allow you to input the conductor size, current, voltage, and other parameters, and they will calculate the voltage drop and maximum conductor length. In conclusion, providing adequate secondary overcurrent protection in 4-wire systems is crucial for ensuring electrical safety and preventing equipment damage. The primary overcurrent protection may not be sufficient to protect secondary conductors from overcurrent conditions caused by excessive neutral current. Therefore, it is recommended to provide separate secondary overcurrent protection that is sized and coordinated to protect the secondary conductors. Additionally, the maximum secondary conductor length should be calculated to ensure that the voltage drop does not exceed acceptable limits. By following these guidelines, you can ensure safe and reliable electrical installation. Understanding the implications of neutral current in four-wire systems is paramount for ensuring effective overcurrent protection. When dealing with unbalanced loads, the neutral conductor carries the vector sum of the phase currents. This neutral current can, under certain conditions, surpass the current in any of the individual phase conductors. This scenario poses a challenge to relying solely on primary overcurrent protection, as it may not be sensitive enough to detect overcurrent conditions in the secondary conductors caused by excessive neutral current. It is crucial to remember that primary overcurrent protection is primarily designed to safeguard the transformer itself and the primary conductors feeding it. Consequently, it may not respond adequately to overcurrent situations arising from unbalanced loads on the secondary side. The impedance of the transformer also plays a significant role in coordinating overcurrent protection. Transformer impedance limits the fault current during short circuits or ground faults on the secondary side, potentially reducing the fault current magnitude observed by the primary overcurrent device. This reduction in fault current can hinder the primary device's ability to trip quickly and effectively clear the fault. Therefore, providing separate secondary overcurrent protection becomes essential. This protection should be carefully selected, sized, and coordinated to protect secondary conductors from overcurrent conditions, including those stemming from excessive neutral current. Circuit breakers, fuses, or molded case switches with fuses are common choices for implementing secondary overcurrent protection. The selection process should consider factors such as secondary voltage, current rating, interrupting rating, and coordination requirements to ensure optimal performance. In addition to overcurrent protection, ground fault protection is also crucial for secondary systems. Ground faults, which occur when a phase conductor contacts a grounded surface, can lead to electrical shock hazards and equipment damage. Ground fault protection devices, such as ground fault circuit interrupters or ground fault relays, are designed to detect and interrupt ground fault currents, thus mitigating these risks. When calculating the maximum secondary conductor length, the formula L equals C times I divided by V times PF provides a valuable tool. Each parameter in this formula plays a significant role in determining the maximum permissible conductor length. L represents the maximum conductor length in feet, and it is the primary value we aim to determine. D represents the impedance of the conductor in ohms per 1000 feet, reflecting the conductor's opposition to alternating current flow. I represents the maximum load current in amps, indicating the expected current flow under normal operating conditions. V represents the voltage of the secondary system in volts, typically a nominal voltage like 120/208 volts or 277/480 volts. PF represents the power factor of the load, indicating the efficiency of electrical power usage. A power factor of 1 signifies perfect efficiency, while values less than 1 indicate power wastage. By accurately determining the values for Z, I, V, and PF, we can use the formula to estimate the maximum secondary conductor length. However, it's essential to acknowledge that this formula provides an estimate and may require adjustments based on real-world factors. Factors such as ambient temperature, conductor bundling, and conduit fill can influence the conductor's current carrying capacity and voltage drop. Always consult the relevant electrical codes and standards to ensure that the conductor installation adheres to all applicable requirements. Furthermore, alternative methods for determining maximum secondary conductor length exist. Voltage drop tables, which provide voltage drop per unit length for various conductor sizes and current levels, offer a convenient way to estimate conductor length. Voltage drop calculators, available online or as software applications, provide a more comprehensive approach by allowing you to input various parameters and calculate voltage drop and maximum conductor length. In conclusion, To ensure electrical safety and prevent equipment damage, it is crucial to prioritize adequate secondary overcurrent protection in 4-wire systems. Relying solely on primary overcurrent protection may not suffice due to the complexities of neutral current behavior and transformer impedance. Providing separate secondary overcurrent protection, carefully sized and coordinated, is essential. The formula L equals C times I divided by V times BF offers a valuable tool for calculating maximum secondary conductor length, but it should be used in conjunction with other methods and considerations to ensure a safe and compliant installation.